Gnanam Paramam Dheyam. Knowledge is supreme.
Okay, so last lectures we have been seeing about field extensions, Galois groups, normal extensions. Today I want to start with separable extensions, and to do separable extensions um, I first digress a little bit on the separable polynomials. So let us recall that we have also used this terminology before. So let f k be a field, this is our base field, and f is a polynomial with coefficients in x, with coefficients in k. So recall that when I write f prime, that is by definition d dx of f. This is a formal derivative of f. Formal derivative. That simply means you just use the formulas like d dx of the powers of x, x power r, that is by definition r times x power r minus 1, and use a linearity. So this d dx is a linear map from the polynomial ring in one variable over k to itself. This is k linear, where the basis element here, that x power r, that goes to r times x power r minus 1, and extend it linearly. So therefore, given any polynomial f, we have another polynomial f prime, and the degree of f and degree of f prime. So the degree of f will strictly be less than degree of f prime. It might happen it is much lesser. It might. So let us list some of the easy facts about this. So for example, let us write it as a lemma. So k field and f belongs to kx, then f prime is 0 if and only if f is either constant, f is constant, or characteristic of the field k is p, which is positive, and there exists a polynomial g in kx such that f will be equal to g of x power p. So only the powers of x power p are surviving as a coefficients of in the polynomial f. Only the coefficients of powers of x power p are non-zero, other coefficients are 0. This is very simple proof. This follows immediately from the fact that if I differentiate d dx of x power p r, this is pr times x power pr minus 1, but p is a characteristic, so this is 0. Therefore, this is a 0 polynomial. So therefore, if f prime is 0, it cannot have power x power I, coefficient of x power I in f is 0 if I and p are co-prime. GCD is 1. Because if I and p are co-prime, these I, when I differentiate this is I times x power I minus 1, and I is non-zero in the field because it's co-prime to p. Therefore, it is immediate from this equivalence. So I leave the details to verify. They are very easy. Okay, now also immediate from this is the following. So another proposition. This says the following: if you have a polynomial K field and f is a polynomial in Kx, remember that our goal in this course is always to study zeros of a polynomial. So, and that includes multiple zeros. Now I am going to reduce the study to the simple zeros. So therefore, we want to state some easy facts about when the zeros can be multiples. So, and suppose L over K is the field extension. And we are looking at the zeros of f in L. These zeros, and among them I look at the multiple zeros. So the multiple, so this is the set of zeros x in L such that f of x is 0. We know there are at most degree f times as many as degree f at most, and among them multiple zeros. So multiple zeros of f in L, this set. So this is precisely the set of zeros of L in L of the GCD. So this is also clear. So proof. So we know multiple zeros are precisely the common zeros of f and f prime. So these multiple zeros of f, this is precisely VLF intersection VLF prime. And also we know this equality will follow from this equality and the fact that GCD of f and f prime, we can always write it as a kx linear combination of f and f prime, where phi and psi are some polynomials in Kx. Both these equality will give you this, so I will leave the details to the verification. All right. So now let us recall, when do you call, so definition, a polynomial f in Kx, where K is a field, is called separable over K. I will drop this over K, always saying it will be understood from the context I write. This is separable if and only if, that this is the definition, that GCD of f and f prime is a unit, that is 1. All right, but this is equivalent to saying obviously that in any algebraic closure, K bar of K, f has exactly degree f zeros. That is, in symbols, cardinality of the zero set of f in K bar is precisely equal to degree of f. This is, then we call the polynomial to be separable over K. All right. So first of all, easy consequence. So note that an irreducible polynomial in Kx is inseparable. When I say inseparable, that means not separable. If and only if f prime equal to 0. This is easy, because if f prime were non-zero, then the GCD will be, if it is inseparable, then the GCD has to be non-constant polynomial, and therefore f prime is 0. All right. So this is okay. Let me write proof. So proof. Let me write a proof. Proof is, so I have to check that I have given that the polynomial is inseparable. Inseparable means there exists a multiple 0 of f. When do they exist a multiple 0? That is if and only if GCD of f and f prime is non-zero, not equal to 1. That is what we have seen in this earlier proposition. This proposition is precisely it's a multiple 0 is precisely the common 0 of f and f prime, and that is equivalent to saying the GCD is non-constant polynomial. That is precisely inseparable definition. But this GCD is non-1 means then that is if and only if the GCD has to divide both f and f prime. But that will mean, and if f is irreducible, so that will mean that the only possibility for GCD equal to f, and then f has to divide f prime, but by the degree ground, that will say that f prime is 0, since degree of f is strictly bigger than degree of f prime. So therefore inseparability of a polynomial is simply tested by computing a derivative of that polynomial and checking whether the derivative is 0 or not 0. All right. So we know about the polynomial being irreducible, polynomial being separable. So now I want to define, so another definition, a field extension, a finite field, it's not necessary, let L over K be any field extension may not be an algebraic. So an algebraic element x in L is called separable over K if the minimal polynomial of x over K is a separable polynomial. But we know this is equivalent to saying that the zeros of mu in K bar, this cardinality is precisely equal to the degree of mu xk. This is what we call the element to be separable, and we will call a finite field extension L over K is called separable if every element is separable. Every element x in K is separable over K. So before we go on to the theorems about separable extension, I would like to give examples of a algebraic extensions which are separable, or examples of the field K where every algebraic extension of K is separable. So, those are precisely called perfect fields. So some examples. First of all, if characteristic K is 0, then every finite extension L over K is separable. That is very clear, because in case of characteristic 0, irreducible polynomial cannot be inseparable. That we have seen, because inseparability is equivalent to saying the derivative is 0, but that can only happen when the field when the polynomial is a constant polynomial. So, characteristic 0 case, every finite extension is separable. Now, two so called perfect fields. So, this is what I want to digress on: perfect fields. So, first definition, and then we will check that the fields are perfect. Okay. So perfect fields means, so you have a field K, and there are two possibilities for us: characteristic K is 0 or characteristic K equal to P. And in this case, we would like every characteristic 0 field to be perfect. So first let me complete the definition. So, and characteristic P case, we have this Frobenius map Fp. Fp is from K to K. The map is any A going to A power P. Remember, this is called a Frobenius. And this is a K algebra homomorphism. That is clear, because we have to check that this respects addition and multiplication. Multiplication is obvious, and addition, because we know it is a characteristic is P. Therefore, A plus B, when you expand by binomials, we get A power P plus B power P. So that shows that this is a K algebra homomorphism, and therefore we can talk about the image of this. The image of this Frobenius in F, these are precisely the elements, P powers of elements in K. This is also, I will denote it by Kp. I will denote this P on this side, because if I write it on this side, one might get mistake with K power P, which is a vector space of dimension P. That is not what we mean here. This is the P powers of elements from A. So therefore, this is clearly contained in K. And now we say that K is perfect. So definition: K is perfect if either characteristic of K is 0 or Fp is bijective. That means, this means Fp belongs to odd K. I made one mistake by saying here this is not a K algebra homomorphism. This is a ring homomorphism. This is a ring homomorphism. all that one can say that this is a ZP algebra homomorphism, Z mod P algebra homomorphism. Because characteristic is P, therefore K will contain Z mod P as a subfield, and as a Z mod P algebra, it's a Z mod P algebra homomorphism. So this Frobenius is an element in this Fp is an element in odd ZP algebra K if it is surjective. This is Z mod P. This is if Fp is bijective. But because it's a field, it's always injective, and therefore surjectivity of Fp is more important. Alright, so that is a field is called perfect if either characteristic is 0 or the Frobenius is a bijective map. Equivalently, Fp is an automorphism of a ZP algebra K. Alright, now we want to, so first of all some examples of perfect fields. So examples, so Q is perfect or any other characteristic 0, characteristic 0 fields are perfect. Finite fields are perfect. Finite fields, no matter what their characteristic is, finite fields are perfect. This is simply because we have to check that Fp is surjective. So if K is a finite set, I know because K is a field and this is a ring homomorphism, this is always injective. And to test a surjectivity in case of finite, if K is finite, it's enough to check that it is injective. So K finite. So the pigeonhole principle will tell that Fp is actually bijective. So therefore, by definition, that finite fields are perfect. All right, at least one example of a non-perfect field. So example of a non-perfect field. Okay, that is, now you take, for example, you take Z mod P and take a rational function field in one variables. This is my field K. Note that the characteristic is K, characteristic is P, positive. Okay, and now let us look at the Frobenius. Frobenius Fp, this is a map from K to K. Any F, any rational function phi going to phi power P. In particular, x is going to x power P. And polynomial, if I have a polynomial f, fx, it is then going to f of x power P. Because this map is ZP linear. So polynomial has coefficients in ZP. If you have polynomial, this is a polynomial in coefficients in ZP. Therefore, by linearity it is x. I know where x go, therefore I know where the whole polynomial will go. So that's it. So therefore I say the image of Fp is precisely, you take all rational functions and take, so image of Fp is precisely Zp of x power P. They are rational functions in the power of xp, power of p power of x. Now note that, Zpx, this contains this field Zp x power p, and this is, I claim that this is non-trivial. So this is not equality here, because for that you just have to check that x does not belong to z mod p x power p. This just follows from the prime decomposition in zp x. So I will not say more about this, but we know now we have this field extension. This is a proper field extension. This over zp x power p, and the element x is algebraic over zp xp, and what is the minimal polynomial? Minimal polynomial of x over z mod p x power p, this is t power p minus x power p. T is the variable I am using because I do not want to use the variable x again, and this polynomial is irreducible obviously. Because how do you check this equality? This equality you can simply check. This is x is clearly 0 of this polynomial, and this polynomial is irreducible over z mod p x power p, and to check it is irreducible over this, enough to note that this is irreducible over z mod p polynomial x power p, and for that you can use Eisenstein. Criterion. We apply it here. This is irreducible, and therefore over rational function field of that quotient field of this is precisely this. Therefore, it is irreducible. Therefore, it is a minimal polynomial. So, therefore, this degree extension, the degree of this extension field is precisely the degree of the minimal polynomial mu x over zp x power p, but this is precisely p. So, its a degree is p. So, therefore, Frobenius map image is not the whole, but it is not too bad, it is only a p degree extension. So, therefore, zp, what we checked is zpx is not perfect. And I would like to write one characterization of perfect field which will be more important for us. So, let me state it. So, proposition let K be a field then the following are equivalent. 1, either characteristic K is 0 or characteristic is positive, P positive, and Fp is bijective. This is the definition of perfect. And second, every irreducible polynomial in Kx is separable. We will see the proof of this soon. When we come back after the break, we will see the proof of this proposition, and then we will continue about our separable extensions, study of separable extension. And the main goal in these lectures will be to prove that a separable extension has a primitive element. Like we have proved earlier, Galois extensions have a primitive element, and now we are proving a weaker theorem that separable extensions have a primitive element. This proposition will prove after the break, and we will continue separability. Thank you.